this paper, we propose a novel 3D space representation method by directly mapping with basic plan units. The plan units are named Planecell for the relation with the output map resembles cells to a living being. Each Planecell is an aggregation of a group of points with similar geometric and color information. The Planecell is efficiently presented by their plan functions, and we adapt a 3-pixel segmentation method to produce the boundary of Planecells. The map displayed is reconstructed from the Kitty odometry dataset sequence 5 with 2000 frames. We then zoom in to see the detailed results. We show you the first 150 frames result. The color of each Planecell is the average of covered pixels. Note that the reconstruction delivers the accuracy of segmentation from another aspect, which is mainly the junction between surfaces. We then magnify the second scene. The scene is a narrow road with white houses on both sides. Four cars appear on the right side of the road. The input of our method is a stereo pair. The output is a 3D representation of the scene with Planecells. Our method starts from the depth calculation. The depth map can be calculated with different approaches or directly inputted at the beginning. We use semi-global matching method for example. With a calibrated stereo pair, the semi-global matching method we use here measures the cost between patches by combining Hamming distances on sensor transformation and gradients. The SGM method finds the minimum path on the cost map with penalties encouraging continuities. Then, by the aggregation of different directions, we obtain the initial depth map. Other depth maps, including the LiDAR ground truth and results from different stereo matching algorithms, can also be the input of our method. The Planecell extraction is implemented with a hierarchical block update strategy, which moves the large blocks first to reduce calculation time. For the reconstruction process, needs to know the boundary of each Planecell. We skewed the boundary update before the pixel level to standardize the Planecell to a polygon with only horizontal and vertical edges. To promote segmentation, we add 2 terms during the update. The regularization term helps reduce complexity. The depth term is designed to combine the influence of disparate information. With the segmentation results, we then perform the 2D to 3D conversion. The boundary of each Planecell is simplified to their vertices. The set of vertices are marked with a symbol strategy, which counts the number of neighboring pixels with the same label. The pseudocode is displayed. For the merging of coplanar Planecells, we propose a conditional random field model, and by minimizing the total energy function, coplanar Planecells are given the same label. Applications like height perception is easy on our map, for each Planecell contains a plan function. The plan function helps calculating the distances, which can be used in obstacle avoidance. The experimental result denotes the superiority of our method. The pixel-level accuracy of our method is higher than most of point-based maps, for the 2D to 3D conversion of our method does not lose pixel-level position accuracy. With high precision, the proposed 3D space representation method also efficiently represents the surface of objects. The map of one frame with a half megapixels only takes about 45 kilobytes. The further work of proposed method is focused on applying more plane models like spheres and cylinders.